title of my talk is about fusion. Ladies and gentlemen, Bournemouth Natural Science heard the first version of my talk on fission and fusion, which led to a new development and a new mission for fusion. We've covered energy from minerals, and I need to change into fusion colours for this part of the presentation. Transformation of elements. Fusion of hydrogen isotopes was discovered by an Australian, Mark Oliphant, in Rutherford's lab at Cambridge in 1934, again with very simple equipment. The first hydrogen bomb was exploded in 1952. As I entered university in 1958, fusion electricity research had been declassified. It was proving too tough to make any of the experiments work properly. There's enough deuterium in the sea to run 20,000 reactors for 4 billion years. This is quite enough excitement for me to want to join the fusion program. I graduated in 1961 and was lucky enough to join Cullum at Harvard. We moved to the brand new lab in 1962. I was the youngest scientist, and the oldest was a charming theorist, Raymond Whipple. He lived nearby. His family is about to celebrate his 100th anniversary. The median age in the laboratory was about 30. Plasma behavior was poorly understood. Everything needed to be invented, built, and put to use by us. The place was on fire with determined creativity and many different approaches. The first director, John Adams, was a brilliant manager and autocrat from CERN and established Cullum as a world centre with many visitors. Deuterium is slow to react at the temperatures we could reach. The easiest reaction to use is the one of deuterium and tritium. And so I have a little model of that happening. If I can have some light. Is this the right model? Oh, this is the right model. Yes, this is the big reaction. And so the reaction is between tritium and deuterium. So there's a deuterium atom and a tritium, and you smash them together, and now it prefers to be helium with the neutrons and protons neatly paired off, and a neutron shoots away at 14 million volts, and the energy gain on this process is 170 to 1. So it's a great way of generating power. A ton of deuterium DT fuel produces 50% more energy than a ton of uranium. It also produces 20 times as many of the magic neutrons. Here is a sample. I brought some tritium for you to look at today. Here we go. And there's a small sample of tritium in this key fob, and it makes the fob glow in the dark. Tritium's got a half-life of 12 years, so it doesn't actually exist on the planet. So it's a marvellous reaction, but we have to actually make the tritium. Unfortunately, you can do that with here I go. Yes. So we start with lithium 6. So it's got 1, 2, 3 protons and 3 neutrons. So that means we've got 2 lovely pairs and an odd couple. If you now bring in a neutron into the lithium-6, it pairs off to make tritium and helium. And so lithium is actually your source of tritium. Now it turns out that nuclear reactors are constantly being moved up and down to match the demand on the electricity grid. And this means when they're turned down, there's a lot of spare neutrons going around which are not being used at all. And so those could well be used by putting lithium-6 rods into those reactors to feed fusion reactors. Okay, so the designers of the Russian H-bomb, Zakharov and Tan, designed a machine, the Tokamak. In 1968, the Russians announced they had reached and sustained a temperature of 1,000,000 degrees in their Tokamak machine, and sustained it. Here's a model in Lego of a toroidal device. You can see the cutaway of the torus clearly, and a magnetic coil being mounted up against it, and some little Lego men around. It's an easy thing to follow. The then Cullen director Baz Pease promptly cut most projects and built the Tokamak, as did every other lab in the world. I set off to Livermore, California, to work on a competing, simpler concept. This lab created the neutral beam fuel injectors, which now power every fusion device on the planet, and it hit 100 million degrees fusion temperature. It opened up supercomputing to the program and developed the first large superconducting coils. Large superconducting coils. The bumblers struck in 1984, and these coils are actually off to the dump. The program was cancelled. Meanwhile, Pease had set up a Skunk Works project with other EU labs to design a reactor, JET. This reached energy break-even by 1997. The design of the next world collaboration was already underway and is now being built in France. Notice the huge size of the machine, the tiny little man, to give you the scale and the size of that machine. It will operate from 2025 and produce 500 megawatts of power and complete the engineering development. But this track will not contribute much to cutting global warming this century. In 2007, I had realized that fission also has a big problem. The world needs about 3,500 reactors by 2050, 10 times the current fleet. But 2,000 could burn the entire world supply of mined uranium. The fast reactors, which can breed fresh plutonium from depleted uranium and burn high-end isotopes, will be too late and will not breed enough. My calculations for fleets of PWR reactors were presented first here at BNSS and at Livermore and General Atomic. My plea was that the only way out was to fast-track smaller fusion machines, refresh the most promising alternatives, and use their prolific neutron output to breed fuel. And so here is the amount of uranium thought to exist on the planet. You've got PWRs, each of which contracts for a 60-year supply of uranium, which exceeds the possible supply by 2030 and crosses over with the reserves in that time scale. So if you really are aggressive with nuclear power and you don't do something else, then you stall the system. Well, that's still bad news for the wonders of nuclear power. Okay, so we need to fast track small fusion. There was no response from Livermore or General Atomic, but at the same talk in Culham, this man, Mikhail Gryazovich, stepped forward. He'd been leading a group of 10 years operating a much more tightly wound machine, the Spherical Tokamak. Here is the now famous picture of the plasma in the first such small spherical tokamak. And it's drawn with a diagrammatic representation of a graphite cover to reflect stray neutrons, a breeding area to make depleted uranium into plutonium, and something to carry the power away. The second version mast worked well and seems to scale up better than the big machines. My calculations with their performance showed that a workable reactor was only a factor of 2 or 3 away in its parameters. Bingo! A new company, Tokamak Energy, was born, together with the best appropriate technologies. Mikhail is standing here beside a set of superconducting coils wrapped around a small tokamak in Prague. A collaborator, the coils are made by Oxford Instruments in this country. By keeping the fusion power below 100 megawatts, the fusion neutron damage to existing steels is tolerable. The latest fuel injectors are available for continuous operation. The first small reactor may deliver only a few megawatts, but a huge number of neutrons to confirm our expectations for the next steps. Of course, a fusion reactor cannot be built soon in the UK, as a warehouse would be needed for all the paperwork. Here is a small tokamak built by Tokamak Energy at Culham, and a little selfie there of my signature on the hull of that machine. Now, investors, because we need a lot of money to move quickly on such things, investors want to know what are the risks. Well, the risks were very high back at the beginning. And there is the big red line of the Russian discovery here, T3, which reached 1 billion degrees. And all the work has reduced the risk down and down, so that we're approaching, when that machine is finished, a 10% probability that anything bad may happen. The small fusion reactors are stepping in here, and they are their risk is dropping as we build all the components and gather it all together, and we end up with a 5% non-technical risk of bumblers stepping in and making life difficult. So the primary goal for small fusion is to breed fuel for global fission. So that is the end of my story of the choices. Renewables are out, nuclear will work if we do all the right things, and the thing which will make it work this century and make it through to all the 10,000 years of possible centuries will be small fusion. Thank you very much. I'd also like to thank the star in my life and my star critic, my wife Maureen.